Okay, this is Mr. Young, and I am going to show you how we can use careful measurements from blood spatter to help figure out where in three-dimensional and two-dimensional space the blood spatter may have originated in a crime scene. Okay, so in Forensics 1, you learned about impact angle of blood drops. You learned that if they fall from straight above, they're pretty much circular, but if they hit a surface at different angles, then they have a more oval or elongated shape. Okay, now in Forensics 2, we're actually going to do some math and figure out some very exact things about the size and shape of the blood drop that hits a surface. And then we are going to use some other measurements and calculations to figure out where in three-dimensional space the blood may have originated. So that can tell us things about where people might have been standing or lying or whatever during a crime scene. Okay, some math stuff. At some point in your math career, you learned about sine and cosine and tangent. And we're interested in the sine of this angle. It turns out the sine of this angle is a ratio. It's a ratio of the opposite side over the hypotenuse. The hypotenuse is the longest angle. So here's the hypotenuse for this blue triangle. Here's the hypotenuse for this green triangle. And here's the hypotenuse down here for this orange triangle. Hypotenuse is the longest side of a triangle, of a right triangle. Anyway, the sine of this angle is the opposite side divided by the hypotenuse side. Okay, let's talk about blood drops. Let's imagine that this is the side view of a blood drop that is flying through the air and it's going to impact on this surface. It's the floor of some room, okay? And so if we put some lines along here to show us exactly where it's going to hit, we can kind of imagine that when this blood drop hits, it's going to turn into kind of an oval stain of blood, and it'll be a little bit longer, okay? And I want to point out some things. Blood drops are spherical when they're flying through the air. So then if we add some more measurements onto this diagram, well, we've got a right triangle right here, and it turns out that this distance right here is the same as the width of the blood drop. And this angle right here, this is our impact angle, okay? Now, remember, the sine of that angle equals the opposite side, that's this right here, divided by the hypotenuse, that's this length right here. So if we look at it from a top view, okay, we can carefully measure the length of the blood spatter, we can carefully measure the height, or excuse me, the width of the blood spatter, and then we know that the sine of that angle equals width over length. Or you can write it this way. The angle itself equals the inverse sine of the width divided by the length. How do we get the width divided by the length? We use those special calipers for measuring very exactly. How do we use a crazy equation like this? You can use a scientific calculator and you can figure out the angle, the impact angle of a blood drop, if you know the width and length of that blood drop. Okay? So the cool thing is, this blood drop, you're doing this measurement after the crime, but this can tell you what was happening during the crime. You can find out what angle the blood was hitting the surface at, which can give you part of the story of where those blood drops may have originated from. So you can look at and take measurements after the crime that can tell you about things that happened during the crime. Okay? Now, in your reference tables, the formula that I just showed you looks like this. Okay, the angle equals the inverse sine of width over length. I would recommend in your reference tables write it this way. So write what is in red. The angle equals the inverse sine, sine to the -1, of width divided by length. Now in your reference tables, they say R equals the width of the blood drop divided by the length of the blood drop, and then they put R into the formula. These are exactly the same thing. I just think that the one in red is probably a little bit easier. The next formula down here we'll learn about next class, okay? Oh yeah, one more thing. Okay, what if you have a blood drop with all these spines sticking off it? And how do you decide what the length of that blood drop is? Where do you measure? Well, here's what you have to do. You have to draw or imagine the end of the perfect oval blood drop, okay? So you do not measure the spines. You just have to imagine, oh, here's where the ending of a perfect oval blood drop would be. That's exactly like this end here. And so the length of this blood drop would just be from here to here, the yellow arrow. Okay? And that is it. Thanks for watching.